Okay, welcome everybody. So today we look again at interfaces, and today's lecture I named Crushing the Interfaces of the Database Management System. And what is the point here? So last time we looked at the outer interface of the Database Management System as it is implemented in our Python database system. And there's, in particular, there's this queryable component. So here we have a queryable component. If we go there, we see, okay, we talked about that last time. There's this unprepared version you should never use, but it still exists in most database systems. Always what you should use is a prepared version, meaning that there's a split in the actual query string and the parameters to the query. Yeah? So these should be passed to this method as two separate parameters, not just one string for the query, but should be really two separate parameters. And if you don't do that, you can easily run into what's called SQL injection. SQL injection, again, is every week there is some company losing data because of SQL injection. And if you have never heard about SQL injection, please read about that. I also have videos on that from the undergrad lecture. It's super easy to get this wrong. It's super easy to miss this and have a huge security problem in your server. Yeah? So you should always use a prepared version, which means there are two parameters. And then as part of your assignment, you also looked into statements like that. So what if you had a method that allowed you to send multiple queries at the same time? Yeah? And I hope you attended the tutorials, and there you discussed that, well, with a dictionary that could kind of work, but there's some issues with that. One being, you don't know about the order of the queries in the dictionary, so that's kind of violating the principle of transactions, that whatever statements you have in a transaction, the database system must never reorder those statements. That's illegal. Yeah? It must be a list, must be a sequence of the individual statements in the transaction, otherwise you may run into trouble. It doesn't mean that you always have to strictly keep the order. If you know what you're doing, if there are no conflicts between two queries, you can also reorder them internally. That's fine. Compilers do that, for instance. Yeah? You write down your program and you assume that statements are executed in a specific order, but most compilers are smart enough to reorder, to say, hey, there's no influence of this statement to statement 1 to statement 2. So I could reorder them or run them in parallel, stuff like that. All kinds of magic is possible there. And the same magic is possible in a database system. But if you want to be careful, and if you don't reason about these reordering statements of an individual transaction, you must not reorder. Yes? They must be executed in the same order, and therefore you should rather use a list interface here in such a method. Yeah? So it's still the old type here, but that should be fixed to have more like a list type, a list of queries you want to execute. And the same for these other assignments. You discussed whether you pass a transaction or a batch of transactions. Whatever you do, you must not change the sequence of statements inside the transaction. Today is about crushing those interfaces. So again, those interfaces were conceived, 45, 50 years ago, and with all the distance, okay, now it's easy to say, okay, there was a bad decision. It's always easy after the fact to say, that was a stupid decision. The interesting thing is to make a decision when you're in this situation, and then there's always someone saying after the fact, but you could have said, this is like the wise guy saying, okay, sure. With all the knowledge I have now, I can make an informed decision and say that this interface has a couple of problems. Yeah? And that is what this lecture today is about, to make you aware of the problems and make you aware of that just by defining the return type, actually, you create all kinds of problems, and you make decisions that are so far-reaching, it's insane. Yeah? So the message I want to hammer into your heads today is really, in case I didn't say it last time already, designing APIs has such a huge impact, and you should be so careful to get them right and think about the consequences. Yeah? And so today I will show you two things that can be questioned here in the standard database interfaces. And one is the question here that may arise, I'm not sure to which degree you discussed it in your in the tutorials, but basically, okay, now I have a method, I can send multiple queries And why would I do that anyway? Because this method could be implemented by a loop. Yeah? So there's a loop that for each query sends this query to the query optimizer, optimizes it, and executes it. So what did I gain in the first place? Like nothing. Yeah? Because if each query is still, from this batch of queries I put into this method, if each query is still executed one by one, I don't gain anything. That doesn't help me. So there is a whole body of work that looks at, okay, why not execute multiple queries together at the same time? It's the same as going shopping. You go shopping, and if you enter the supermarket, you could go to the supermarket, get this one item, this one apple, and then go back home. And then, now I also have to fetch the banana. You go to the supermarket again, get the banana, go back home. You need some muesli, go to and so forth. That's stupid, because all the traveling back and forth, paying at the cashier and stuff like that, there's a lot of overhead involved. Yeah? So, of course, what you do is you share your shopping. Yes, you buy multiple items at the same time, in the same batch. Yeah? You share the effort. You share the effort for going to the supermarket, not just for one item, but for all of them. And that's the same idea here. Why not? So if I have to execute a query, if I have to read a large input table, why not share the work and answer multiple queries at the same time? And that is what's called multi-query processing or multi-query optimization. So in contrast to what we did in the undergrad lecture, there it was always one query at a time. Now we look at multiple queries and execute them together. It's a pretty interesting concept, actually, and it has far-reaching consequences. And we have a notebook on that. We can make it a little bigger. Can you see it? So same notebook as before, the same fake data we are creating. So a couple of relations here. I still have my phone on. Shouldn't do that. So, so a couple of tuples we create in a list, of type stuff with two attributes only, attributes A and B. And now I want to scan this. So I want to scan this and filter. I want to have a certain attribute and I have a certain constant I'm looking for. So I want to have all tuples where the A attribute equals 7. A simple equality search where A equals 7. And you can do that easily by such a method. You input the data. You have your criteria, attribute and constant, and you return the list of stuff. So obviously, what is being returned here is a subset equal the input data. And it's implemented super easily. What you do is, okay, I initialize a list. That's the result list I want to return. And then I loop over the input data. Again, this is a weird notation for type hints. So the type hints for the variable of a loop has to be declared before. It can't be done within the loop. So this just says for type hinting, the element assigned, so this the item assigned to this element variable is of type stuff. What you do is then you evaluate the predicate through some Python magic. So basically directly access the internal dictionary, check whether there's an attribute named attribute, like this small a, and if that is equal to the constant, and only then I append it to the result. So loop over the data. If the predicate is true, append the tuple to the output result set. I think you won't find a simpler algorithm in this lecture anymore. Yes, can I think about a simpler algorithm? Not really. Projection push down. No, that's the simplest algorithm you will ever see, okay? You can execute that, and that's what we do here, and then you get these results. So it's 3 results you see, A equals 7, A equals 7, A equals 7. But then the question is, okay, what if you have more queries? What if you have a couple of these queries all on the same relation? For the moment, it's just one relation. So one relation stuff, all of these filtering on could be the same attribute, could be a separate attribute. So I could do it like this. I could do one scan call per query, for instance. So that's what I said before. Well, there's a loop. So if you put your queries in a dictionary, so that's query name, and then for each query I keep a dictionary as a value that says that's the attribute and that's the constant. So basically all of this stuff is a condition here, the filter condition of the query. So what I could do is I could basically loop over the dictionary items and then as before call scan once for each query, right? Looping over each and individual query. Yeah, that's clear, right? Yeah, okay. So I do that here and then I get the result. Again, for Q1 it's hopeful, I think it's the same as before, a equals 7, right? Yeah, should be these 3 tuples are returned. I can make it a little bigger. These 3 tuples are returned. For Q2, what's the condition again? B equals 32, it's this one. Then B equals 1, it's those 2 tuples. Yeah? But again, recall that for every call of scan, we loop over the entire table. We have one loop. Yeah? So it's for each of these queries, it's linear costs for looping over the input table. And the problem, of course, is so database people always love to worry about scalability. So the question is, okay, what if the input tuple is like 1 petabyte of data? Yes, that means now I have to scan 3 times 1 petabyte is 3 petabyte. And we haven't touched on that so much here in this lecture. We will go there in a couple of weeks. But fetching data from storage is always incurs some cost. Yeah? It's not for free. Yeah? If your data sits in memory, it's kind of for free. But if you have to fetch it, be it via the network, via the internet, via some storage service, via tape, disk, or SSD, or whatever storage medium you have, that incurs some cost. And we want to avoid these costs. We want to avoid doing it multiple times. Yeah? So one idea you could do is, well, why not scan it once and check the conditions of those queries all at the same time in a way? Yeah, that's what we're doing in this next method. That's called a shared scan, or that's one variant of a shared scan actually. And the change to the scan above is, here we do not only enter attribute and constant, we enter the dictionary of queries we want to execute. Yeah? And then as a result, it's not only, if you go back again, so here the result was just the list, yeah, this list of elements that qualify for this particular query. The query is here denoted by attribute, comma, constant. Now I have multiple results, of course. For each query is a separate result list. Yeah? So somehow I have to represent that in my API. And that's what I'm doing here. So I'm returning a queries dictionary. So let's go through that implementation. So I create a result dictionary, not a list as before. I have a dictionary where this string is the name of the query, and the list of stuff is the result list for this particular query. And I initialize this with a dictionary where I just simply loop over the incoming queries dictionary. So the query, if we go back here, so that's the queries dictionary. So here I have the name of the query, and then I have the dictionary of the parameters. And now what I do is I loop over that in this. So this is a dictionary comprehension, same as a list comprehension. So I initialize the dictionary, that's a squirrely bracket, and I say, okay, the key is whatever key I have in the incoming queries dictionary, so the name of the query, and that maps to an empty list, empty result list. So basically for each query in the incoming query stick, I initialize that as a mapping query name, Q1 maps to empty list, Q2 maps to empty list, Q3 maps to empty list. And then I loop over the data as before, but now what I do is, inside the loop, there's a nested loop. So whenever I have one element in my hand, I check for each and every query whether it qualifies. So rather than just checking one query, I now check for each element the 3 queries. This could be more, of course. The 3 queries are coming in. So this is the same check as before. However, now that this check is nested in a loop. Yeah? So this is doing a loop for each query. If you go back again, you see the contrast. Here there was only one loop, looping over the data, and then as I only have one query, I could also have looped over the list of queries, which is of length 1. Yeah, it's the same thing. So basically, if you just kick these elements out, yeah, these two, It would be the same result, of course. Yeah, but I'm processing multiple queries at the same time. And whenever this condition holds here for a particular query, I append the result not to a global list, but to a list for this specific query, for the result dictionary. Yeah, so if I have one element and it qualifies for query 1, I put it to query 1. It doesn't qualify for query 2, so I don't put it to that result list, and so forth, and so forth, and so forth. Yeah, yeah, and if I run that, I get something like that. So I get a dictionary, and I have, now I have these elements returned for query 1, those for that, and that for that. Yeah. So from the result point of view, it's the same. And actually, there's a unit test down the road in the notebook that checks that it actually is the same. Yeah. But what I saved is, I only ran the loop over the data once. Yeah. I processed the data only once. So can you imagine any other situation in data processing where an algorithm like that may be beneficial? What kind of real-life situation would benefit from something like that?
Someone is looking for
always like that, and then, yeah, okay.
When someone is looking for some specific picture on Instagram and you have to serve a lot of people the same thing.
Yeah, actually work sharing among multiple users. Yeah, so if people do the same thing or do similar queries, doesn't have to be a database query, it can be whatever, picture search or whatever we had the last time, all the different types of queries you may have in a system like that, you can share the work. Yeah, that's correct. Any other ideas with something like that, what you could do? Yeah?
So when the table is large and we only need to load the table in the RAM only once.
Yeah, that's right. We only have to need to load it once. So what could happen in a system is you want to evaluate one query, you load it into RAM, then you do some other stuff, which you unload the table or it's overwritten by some other data. Next query comes in, you load it again. Yeah, but that's the same effect as so it's more detail on, okay, you have to reload the table. You have to perform what we call I/O, input-output operations. We read it from some slower medium into DRAM, from SSD to DRAM, and that incurs some cost. In this approach, I don't have to do this. I just do it once, execute all of these queries, done. Yeah? Does anyone see a drawback with something like that? Yeah, maybe. I was just waiting for them. Yeah, but okay.
If we get a large amount of queries at the same time, then we have to traverse it for a lot number of queries. This whole data.
Yeah, so there's of course an added complexity. For each element, I'm running the loop. Yeah, so that could add to the complexity and is an additional CPU effort. So the idea here is that I'm saving on I/O effort. In other words, on looping over the element, where is it, in data, I want to save on that, I only do that once, and I pay a price that I loop here on the queries. Yeah? But if you think about that, you would do that for the individual query execution anyway. Yeah? So there's the loop of size 1 for each query you're looping over. I'm not sure how Python handles that, so the effort is still kind of there. Yeah? And one rationale behind that is also that typically I/O time, I/O is so much slower than the CPU. Yeah, so you will see many algorithms in this lecture, but in general in databases, that optimize on I/O, that optimize on not reading so much data, yeah, not transferring so much data, at the price maybe of investing some more CPU time. Yeah, that's a good deal in many, many scenarios. Yeah? You can't spend too much CPU time. You wouldn't be able to run whatever some deep learning algorithm here, some backpropagation or whatever, that would kill the CPU, of course, probably, yeah. But easy stuff that doesn't cost too much won't hurt you. That's a trade we typically do in database systems. Okay, but from the point of view of the user, does anyone see a problem here?
So if I batch a lot of queries together, then it's not happening that the first query is finished in the same time. So it will finish slower because all of the queries will get batched together.
Excellent, yeah.
longer for the first one.
Right, yes, so the normal single query at the time processing works like this. You send the query to the database and the database immediately starts executing the stuff. You immediately get the result. But here, you first have to form the batch. You have to, whatever your decision is, to form those batches, yes, these piles, these lists, or here it's a dictionary of queries. Yeah, so it's not executed immediately. The query comes in, and after a certain time, for instance, could be that after 30 seconds, the database system decides, okay, whatever happens, now every 30 seconds I send a batch of queries to the shared scan and execute it. This means you add this wait time before the query gets executed to the individual query. So that there's a price you pay from the point of view of a user. It's not executed immediately, but it's, it has to wait till it is part of the batch and the batch is being processed. Right, still could you see, what does it mean if you contrast that with individual query processing? This wait time, yeah? So you add an extra wait time to the individual query, or most of them, yeah? And the last query that comes in, maybe that closes the batch gets executed, so you don't have an extra penalty there. But in general, you will add some wait time. Is that bad or good, or what is the trade-off here? If you confront that, if you contrast that with a wait time you have while doing individual queries, how would you do individual queries? A petabyte of data, one filter at a time. What is the wait time for the query? If the system is available, the wait time, if the system is idling, the wait time is 0. Yeah? But if you scan a lot of data here, you have a great likelihood that the system is working like crazy. Yeah? If the petabyte scan is already going on for one query, and then the second query comes in, the second query has to wait in that scenario anyway, because the system is busy. See that problem? Yes, so one query comes in. Yeah, you see it when you write it on the timeline. So query 1 comes in and processes like crazy, like whatever, 10 minutes to scan the petabytes, 10 minutes. Here query 2 comes in. So what can query 2 do? It can't do anything because it has to wait for query 1 to finish. Right? So you have wait time here anyway. Here's wait time. Sorry, there's wait time. And the other argument we had in batching, okay, in wait time, now the query isn't executed immediately. Individual, and this is batch. The query isn't executed immediately, but you first assemble a couple of queries. Yeah, maybe it's just the 2 queries, and then you start processing. So this could be that the wait time of this second query is actually lower in batching than in the other approach. Do you see that? Yeah, and that's something you have to balance somehow. Yeah, you can by setting the parameters when to close a batch, when to execute a batch, and so forth. Anyway, we will get rid of batching in a moment anyway. But for this algorithm, you have this problem. And in general, you have this problem for batch algorithms. Yeah? So there are many scenarios where you use batching. For instance, when committing transactions, we will look at that later on. You don't commit transactions individually in a system. You always commit them in a batch, and there's a trade-off for that. Yeah? So there's always something you pay as a price, but it may still be that you gain over executing it individually. Yeah? So the interesting thing is, can I gain in throughput? Can I process more queries at a time in this approach or in that approach? Yeah? And often the argument is, of course, you want to improve throughput. So there's a number of queries processed on average in a given time unit. Okay. So this is one variant of shared scan. We look at 2 others. And the second is, so you could argue here, so for each query you materialize a list. You output a complete list here. I mean, okay, those could be references to the same instance, and it's a bit cheaper. And I think that's what Python does here. So the object is not copied. There's no copy on the object. So if you put in, here's an example. Here's this A7. That should be the same instance in Python when I implement it like I did here. But another variant you could do is what's called tagging. So in tagging, that's a variant where, again, I loop over the data, but I don't create separate lists for each and every query, but I just tag it with a label. For each, you see it here. So here, my results are is an element of class stuff, and then I have a list of query names. This signals, okay, for those queries, this element of stuff is actually a result. Yeah, so rather than producing a separate list for each and every query, I do one list, and then for each element in that list, I mark whether it's qualifying for a specific query. And only if it qualifies for any element. Yeah? So maybe we briefly go through that. So for each element in the result set, I create a new list of the queries where that is relevant for. Then again, I check all these entries from the queries dictionary. If I find a result, so the attribute matches the constant, then I append it to that list. So this is a query name being appended. And once I'm done checking all queries for this specific element, the last thing I do here is I append it to the output list if this element was relevant for at least one of the queries. If it wasn't relevant for any of the queries, why would I put it to the output, right? And when you look at the result, that's something like that. So you get a list of results, and here you have, okay, this tuple, and that is a list of queries where this is relevant for. This is only relevant for query 1. This is only part of the result set for query 1. Here you see a different example where this tuple is relevant for both of these queries. Yeah, like that. It's basically like putting a label on. If this is my tuple, I put a label on the tuple saying, okay, query 1, query 2. Yeah, for each of those, there must be at least one label in the result set here, saying, okay, that's relevant for this, for that, for that, for that, for that. Yeah? So like that, I can. I don't have to duplicate the result list in a way. Yeah, and then I wrote a helper method here where I convert this format back to the format we had before. So from this format, I want to go to this format again. Yeah, that's the one where I have a separate list for each of the queries. Why do I do that? Why would I want to do that? Yeah?
So instead of a few of the first list, like result and relevant queries, just return the same format. So for one query, we return one list.
Right. That's what I'm doing here. So basically the format on top, here, this one, yeah, that's what I just said, this tagging format from this shared campus tagging. I put that into this method, and this method converts it to the other format that was created by this first method. This other shared scan that creates individual lists. But the question is, why would I do that? Just for having a nicer output? Yeah?
This is the natural way how variables are returned for each query. You get the set of all results.
Yeah?
If one central result, then you can't really add
Right, very good. So if my interface wants that for every query now I return the actual result set, I mean I have to conform to that interface. That's true. Yeah, that's one thing I do. Very good. Some other ideas? Yeah?
We want to work on a query based on some result from an existing query.
Uh-huh.
Like for a new query, you work on something that comes from an existing query. Instead of reperforming that query, you can just take the result in the list and go through it.
Yeah, I'm not sure whether I mean, of course, it goes along the lines what your colleague just said. I mean, this is an internal thing, processing multiple queries at the same time. The outside view is there's one query that wants to have one result, so I have to be able to return a result list of some sort. Yeah, it goes along the same lines, yeah?
Another thing is that the first format gives us information about what other queries it's relevant to, and we do not need that information.
Yeah, that's true. You don't need that from the point of view of the individual query. I really don't care who else is, it's again kind of an isolation property. Yeah, I don't care who else is interested in the data. I just care about myself. Well, that's the point of view of the query. That's true. Yeah. Any other ideas? And maybe there's a hint on the screen. For testing, of course. Yeah. So I want to compare my two algorithms. Whenever you have two algorithms computing the same stuff, hey, end-to-end unit test is there. Great opportunity. Yeah. First thing you do to not get in trouble, and that's the reason why I actually did it. I mean, you're right with okay, the user side wants to have a list. Yeah? You said it both in different terms, but my rationale for doing this here was no, I want to unit test this stuff. What the heck? I mean, this is a simple algorithm, but of course, simple algorithms will get wrong. And that's what I'm doing here. So the test is cross-testing basically the individual scans. That's this one. Here the scan method is called in the dictionary comprehension. Compares that with a first shared scan method, and then again it compares it with a second shared method. Yeah? Compares result sets. Yeah? It's a kind of a brute force test. I don't know, checking here 2,000 elements, and I think I is a number of, I sent 30 queries here in the test. Yeah? I mean, of course, it's not comprehensive. It's not thinking about edge cases and writing unit tests. A good, more fine-granular unit test should think about the edge cases where things can go wrong. That's fine. But this gives you a first indication, an end-to-end test. Yeah? And it's so low-hanging fruit. Yeah? Whenever you have a join algorithm, how would you test a join algorithm in a database system? And what is the end-to-end test for a join algorithm in a database system? So we learned about joins in SQL, relational algebra. Yeah, there are some algorithms implementing those joins. How would you end-to-end test them? Yeah?
The results and the time that needed to be joined together.
The time? The time you don't need. But the results is okay. So you have two join algorithms, compare the results set should be the same. Yeah? The time doesn't matter because it's just about correctness here. Yeah, that's okay. So if you don't have any join algorithm implemented, what is your baseline? How do you compute the baseline results to compare your first join algorithm with? Yeah?
When you do like manually joining it and you get the result from
No, let's say you have really two tables, each has 1 million or whatever, 1,000 entries. And now you implement your first join algorithm, and they want to check whether your join algorithm returns the correct result. What is the easiest way of doing an end-to-end test for that join algorithm? Yeah? Yes. Yes. Excellent. Yeah? Recall joins are just syntactic sugar for cross product followed by a selection on the joint predicate. Yeah? Square complexity. Be careful not to have the result sets shouldn't be too big, otherwise they will ruin everything. But for small input sets on modern machines, who cares? Yeah? It's super fast and gives you very quick indication. And the great thing about that is cross product plus a filter works on any predicate. Join algorithms typically only work on a specific predicate. Equality joins, for instance, yeah, along foreign keys. It's a very restricted subset of the joins. But you can compare against the cross-product result. And how do you compare a cross-product in Python? A for loop? Yeah, but we have two relations. So how do you do that? It's one relation, one loop. Yeah? What's the relationship of the... For R in R, for S in S. Joint predicate. Joint predicate. Evaluate R concatenated by S. That's what the cross product does. Combine each element from R with each element from S. This leads to something which is called nested loop. A nested loop. Yeah? It's actually an algorithm, nested loops. Nested loops join. Yeah. If the predicate qualifies, yeah, if output a join result at that point in time. That's the cross product. Square complexity, obviously, number of elements in R times number of elements in S. It's not going to scale, but for testing purposes, awesome. Yeah. First thing you do. Okay. Right, so this is scan with tagging. So again, so the bottom line of this notebook is you can execute queries individually. That's the first algorithm we looked into. Here, individual scan. You can also share the scan, build separate lists for each of these queries, but only scan the input once. Or an alternative to that is that you just compute one output list for each of the queries. An element is in that list if it is at least part of one of the query's results. And then you have just a tagging mechanism. So the tagging mechanism that we use here, so I use a label of the query, could also easily be replaced by bits, bit lists of some sort. If you look at bit list indexing, I think 1 or 2 weeks from now, maybe then we can revisit that. But the core idea is always it's a tag, it's a label. I'm labeling this result with, this query. For this query, this is a result. This is a tuple that's part of the result. And we looked at this batching problem. Yeah? Now I want to show you a shared scan that doesn't have that problem. And that's called, where is my, here we go. Why doesn't it work again? Only works on. You always have to have a backup, right? Okay, so this pencil works, the other didn't. Let's call this a clock scan. That was invented multiple times in database literature, but the idea is awesome. So the idea is, so typically we regard problems as there's a query coming in, and then we have to do some stuff to process a query. But in this algorithm, it's like we do some stuff, and if some query comes in, maybe we can attach the query to doing some stuff. So the core algorithm is scanning the table at all times. So if you have a petabyte table, you scan it. You just start scanning, whether there's a query coming in or not. You just scan the table. And when you're done scanning the table, you start all over scanning. And if you think about that, you can map that to a circle, to a clock. You scan around the clock. So if this is basically the start of your scan operation here, yeah, that is 12 o'clock. You keep on scanning until you're done scanning the table. Yeah, so we make one round around the clock, and then you start scanning all over again. Now we had this batching problem that the query has to wait till, what was it here, till a batch is formed. Here it's kind of different. Here you say, okay, no, whenever a query comes in, and here I think query 2 is an example. Yeah, if a query comes in, you're basically at the current time, at the current position in your scan. Yeah, I could say this is roughly, I don't know, 5 o'clock in a way, 5 a.m. or something like that. What you do is, the scan is going on, and basically you attach the query to the ongoing scan, and the only information you have to make sure is, okay, this query was now attached at 5 o'clock. It also has to be detached at 5 o'clock, because the invariant is each query has to see each tuple exactly once. So that translates to each query has to make one round, one scan around the clock. But that does not imply that each query has to start at 12 o'clock. You can start at any time, at any position in the circle, scan around the clock, just make sure that you leave at that precise time again. Yeah? Other than that, it's the same shared scan algorithm I just explained. It's not forming batches, but just running the scan at all times, a continuous scan operation. And once a query arrives, you attach it. Yeah, if a new query arrives, you attach it. So here, assume this would be query 3, Q2 is still ongoing. You scan, maybe here another query arrives, query 4, and so forth. Yeah. When you're here, you have to detach query 1. Query 1 has to be removed from your scan. When you're here, you have to detach query 2, and so forth. Yeah? So that guarantees that each tuple each query sees each tuple exactly once, and it guarantees that each query processing starts immediately. Yeah? See that? Makes sense? Cool algorithm, right? It's a simple algorithm. It's so simple, but it solves this problem of the wait time. Yeah, you don't have to wait anymore. You start processing directly, and you still share the scan. It's awesome. Super great idea. What did I want to say about that? Query scan. Also, no, here. Attach and attach current at any point in time. Yeah. No, that's all I wanted to say about that. There's a paper reference here. If you're interested, there was concurrently another paper I didn't mention here, but that's basically where I took this graphic from. Yeah, so that is one way of processing queries if you are in a mode like here in our, where was I? Am I again in the wrong window here? Interesting. Here, no? So that's basically this, what we talked about. There are multiple queries, and now what I showed you in this first hour of today's lecture is, there is opportunity for executing queries at the same time. Yeah? So this could be, if it's factored in the database, in the API, you could do something like that. So what if your API doesn't offer that? Can you still do something like that? So if your interface is still like there's one query at a time, what does it mean for the shared scan algorithms? Can you do a shared scan? So if you only have this one query at a time interface, yeah, this one, or you can't? Yeah?
I mean, you could merge the predicates into one big predicate and then on the result separate them again.
You mean outside?
Yeah, after
Yeah.
you retrieve the results.
Okay, yeah, that's true. But from the point of view from inside the database system, yeah, so we get all of these requests for individual queries. Could we still do something like a shared scan or this clock scan without having the interface allowing users to send multiple queries at the same time? One query at a time is coming in. Can you still do a shared scan? Yeah?
Yes, because it's just interface, so the background
Oh, please don't say it's just an interface.
Do batch internally
Yes,
and do the clock scan.
right. You could do that. You could collect queries, yeah, do the batching, or do the clock scan whenever this stuff comes in, but translate it internally into not calling the query optimizer every time, but doing a clock scan stuff. Absolutely right. Yeah. So for this scenario, it would actually work. But of course, it's always better if you also have it explicit, then you give a hint to the database system that, it's a batch of queries, hey, you can really do, and I expect you to do some sort of multi-query processing. Okay, the other part of the, it's just an interface. I don't get over that. Who said that? Just an interface. I know this attitude. I know this, but really don't. It's insane. Yeah? I will show you more examples what you can do with it. It's crazy if you really spend. I mean, it's also it's from the point of view of investment. Think along the lines of that. It's just an interface. Yeah. Yeah, it's some I have to have a function call for the user for my great algorithm. But what you see so often in program is when you think about that and get the interface right, you save so much work. It's insane. And you make your software so flexible in so many cases. So rather than having to work around the shitty interface later on, getting the interface right is magic. Yeah? I think there should be there should be a museum for great APIs, actually, in a way. Yeah? So, really, literally, yeah, because if you get that right, yeah, you often also solve algorithmic issues and so many issues. Yeah? It's really always an amazing experience. Yeah? And it's an art. It's really an art form. Well, computer science is an art form anyway. Okay, so now we looked at one query, where there's multiple queries. Now let's look at this stuff here, an iterator of objects. So in the SQL world, that means you send a select whatever query. You join on as many relations as you want. What you return is a single table, a single relation. So SQL statements always return a single relation. That's carved in stone. That's how it was conceived in the 70s and 80s by the inventors of SQL. And I want to question that today a little bit and explain you why it makes sense to question that. And this is joint work with two of my PhD students. And the question is, what if a SQL statement returned a sub-database? So not just a single relation, but somehow a subset of the underlying database. What does it mean? And again, this is basically just changing the return type of the interface. Yeah? If you go back to our PyCharm, so what I will be changing is I don't return an iterator of objects, which means I don't return an iterator iterating over the tuples returned on this table that SQL produces. But what I'm changing this to is something like that, sub-database. Yeah, so you send a query, and what you get is a database as a return, a sub-database of some sort. Yeah, that's what we will be doing in this second hour. And if you think about that, I think a good analogy is this video I found. So if you do something like that, select like the dark, you have two relations, dark and white, and here you collect something from some columns. Yeah? You specify some columns you're selecting here. So there's all the columns from the dark relation and just one column from the white relation. What the from actually does it puts this together. Yeah? So if you have two relations, you already are in trouble because, so what does the from do in SQL? What does it do? What's the semantics of from in this statement? There's only a select, there's only a from. What's going to happen? Yeah. Cross product. Super crazy. Yeah, it's not explicit in any way in SQL. It's just a cross product is happening. So each tuple from dark will be combined with each tuple from white. Yeah? So there's a lot of combinations and redundancy possibly being created. Yeah? If you have a join condition on these two relations, what you typically have, typically you don't want to have a cross product, but you have such a condition, then you feed that into a join operator. And the join operator only gives you the tuples that are qualifying. We had this discussion in the first part of this lecture. So join operator is typically way more efficient than just doing a blind nested loop. Yeah? And what you could also do is you can filter out some of the tuples. That's what we're doing here. So whatever is produced here, we just are interested in some of the tuples. Yeah, only the tuples where dark.e equals 42 should be returned. And overall, it's something like that. So you collect columns from these relations. You collect all columns from the dark table, or maybe one column from the white table, and then you compute a join. And maybe there's also a join condition I forgot here. It could also be a join condition. And then whatever comes out of that is glued together, yeah, as one big table. That's the output of SQL. Yeah? So basically, the SQL output is something like that. You have values from all kinds of tables, some from the dark, some from the white, and so forth and so forth. Yeah? And that's basically the analogy that explains what SQL does. So for instance, maybe I have the example later on. Basically here in this table, you see it already. That's some output table. We will go into what the SQL query behind that actually does, the SQL query that created that output. But here you already see some redundancy. So there's Professor A appearing twice, Professor B appearing twice. It's this kind of redundancy. Yeah? So in computer science, it appears twice. We don't really know whether that was generated from the same name or not, but it could be redundancy. Yeah? And the same happens for this wooden board. And yeah, I bumped into this when working on our master application system, actually. What I was trying to do is what was a list of applications for a specific study program. And they already saw that, okay, whatever I would send to the database system, it would only return a single table. And that was kind of not what I wanted to do, yeah? Because I wanted to have something that looked tabular, like in this output, but for each row I also wanted to have associated instances, and that didn't really work in this world. There are many occurrences of this problem. So one is when querying hierarchical data, there's for views, materialized views, logical data independence, access control, and distributed systems, where this problem actually happens. So we will have a separate notebook later on for distributed systems, what you can do there for these kind of problems. Progressive web apps, that's a kind of application. So typically you have your phone and there's an app on that phone, and the app works super well once you are once you have internet. But what happens if there's no internet? So typically most apps break down or reduce their functionality dramatically. The idea of a progressive web app is that even though you don't have an internet connection or you only have a shitty internet connection, the application still works. You can build applications like that to a certain degree, and there this problem also occurs. So what is the problem? So this is a problem statement. So I have an end-to-end relationship. So basically I have professors and lectures, and they're connected through this give relationship. Maybe I switch to my other device and I can scribble a bit more on that. Here we go. So we have professors and lectures. They're connected through an end-to-end relationship, so professors give lectures. Yeah? And what I actually want to display is something like that. It's something already hierarchical. So Professor.A gives lectures computer science and gives the lectures database systems. And this is the relational model and the sample data, basically, we have in our database. So a couple of professors, a couple of lectures, and then the end-to-end through table or connecting table connecting professors with lectures. Now the question is, how do I even retrieve the data, and what can I do on the database side? So the solution to retrieve the data is this statement. This statement produces the results I just showed to you. So I want to have data from all of these three relations. I specify the join keys here. I say the difficulty should be low, and then I say, okay, that is the columns I'm interested in, those 3 columns. Yeah? I also order by a professor name, yeah? And then I get a relation like I showed to you before, basically this one. Yeah? So there is, everything is flat, yeah? So the professor A was spelled out multiple times, this lecture was spelled out multiple times, and so forth and so forth. Yeah? That's basically the result table. And that looks easy, but it has a couple of problems actually. And the problem one is what we call in databases denormalization or data duplication. Yeah? So here the professor was duplicated. This value was duplicated in result set. Here the same, again, here the same. All values here that have the same color basically are duplicates from the point of view of the database. And that's pretty weird because one of the big design goals of databases is to avoid redundancy at all costs. So you should not store data redundantly because that leads to all kinds of problems. If you have the same information stored twice and you update it only in one place and the second says, no, it's something else, whatever. Yeah? So one super important design goal of a relational schema is to avoid redundancies at all costs because that will lead to problems in application development. Yeah? So you shouldn't do that. But if we query the data with SQL, we do the opposite. All of a sudden, there are redundancies. Why the heck is there redundancies? Yeah, I mean, it completely violates everything we learn in anti-relationship modeling and relational modeling. Yeah? So this denormalizes the data. Denormalizing, you can vaguely translate to it introduces redundancies. Yeah? That's not what we want to have, actually. And then there's transmission cost. Yeah? So if you introduce redundancy, so you have to transfer the same data multiple times rather than transferring it once. Yeah? You pay a price, additional transmission costs. Yeah? So this Prof A here has to be transferred twice, computer science the same. Of course, you can then throw some clever compression algorithm at that. We will look at how you could compress these things later on in this lecture. There are very nice techniques that allow you to compress data and then have less I/O. However, it's already rotten from the start. It's already, why do you create these duplicates in the first place? And the impact may be the transfer costs for result sets between the database and the client. And the larger the result table, the higher those costs. And the more end-to-end joins you have, the higher the likelihood that you have these redundancies. And this feels weird. And the other thing is, and that's the stuff I bumped into when developing this application, is you have to renormalize. So you get the denormalized data, but I want to have something like that. I want to have something like, okay, I have one entry, maybe one row in the UI, and then I have like sub-rows in a way, listing all the lectures like computer science and databases and whatnot. A hierarchical display, and that's not what I get from the SQL result. From the SQL result, I get this flat representation, one tuple, one tuple, one tuple, one tuple. That doesn't match what I want to have. Yeah? So I have to provide some code in the application as the application developer to get back to a display like that I actually want to have. So that's an additional coding effort, and of course, it's also a point where you can introduce bugs. Yeah? The fourth is intermediate result sizes. So if you remember that from our BDE lecture or some other lecture from wherever you came from to this university, we will look at that later on also in this lecture. But when you process a query, you create temporary intermediate results. Yeah, and these intermediate results already blow up due to these redundancies, due to duplicating data. So it's not only when transferring the data to the client, it's already in the database system that you blow up the data set artificially with these redundancies. And that's a bad idea because it leads to all kinds of extra costs in terms of CPU, main memory requirements, and so forth and so forth. Yeah, and then another interesting thing is you lose information about the schema, about the underlying structure of the database. Yeah? So if you just look at the result, you don't really know, do these two database lectures belong to the same entity in the underlying data model, or is it a name clash? I mean, in theory, it could be there are 2 lectures named computer science. Do I know from this output? I don't. Yes, no one can tell me without looking at the database whether that is the case. Could be the same lecture given by both lecturers, both professors A and B, but it could also be a separate lecture. Huh? So there are workarounds you could do. You can project out primary keys, check whether the IDs are the same, but it's a workaround. Then you also lose all information about keys. So recall in relations and ER modeling, we introduce keys. There should be a key, yeah? Making sure that this combination of attribute values is unique in your data. There's no notion of keys in the SQL result set. Even though it's kind of a relation, it's kind of a table, there's no concept of a key. It doesn't mean anything. It's not even defined. It's not a proper schema definition for the SQL output. Yeah? It just simply doesn't exist. Yeah? And which is wild because, okay, it's outputting a relation, but it's not a key? What the heck's going on here? Yeah, and that also is true for all other information that's in the schema. Yeah, so here it's just the names give you some indication that, okay, if you just look at that, aha, P probably means professors, right? So I guess this was the name of the professor. Yeah, it is professor.a. But what if you have 10 other relations that start with the name P and use that abbreviation in some query? Yeah, you should know your schema. Maybe you have to look at the SQL query to understand, but there's a lot of room for misunderstandings here. Yeah? And this one is a bit more involved. Actually, when you think about that, so in SQL, you only get a bunch of data values in rows. That's what you get. Yeah? And there was quite some work in the 90s. In the 90s, object-oriented programming languages came up. And people were questioning whether the relational database systems were the right fit for object-oriented models. Yeah? And then extensions were developed, like Postgres, for instance, has many extensions for object orientation. All of this basically didn't really work out. So today, the industry standard is still relational database systems. There are few niches where object-oriented database systems are used, but it's really niches. Huh? So the winner is a relational system. But there's still this weird mismatch. And you see that when working with relational systems or working, for instance, with Django, yeah, with objects in Django. We learned about in BDE, there's this Django ORM, Object Relational Mapper. So you have some relational data, and you hide it with your ORM and translate it into instances, which are objects in a way. Now, feels super weird, leads to all kinds of confusion, but it's a good approach. Yeah? Don't get me wrong, but you have to translate it. But actually, when you think about that, the entity relationship model I claim is already an object-oriented model. Yeah? And the problem only occurs once you start translating entity relationship models into a relational model. There you lose everything. Yeah? That's a big problem. But at the end of the day, this is already an object-oriented model. Yeah? And yeah, if you combined that with this idea to return sub-databases, you would actually, yeah, you would solve all of these problems. But it's a longer story, actually. Yeah? But just wanted to mention it because I believe this approach also solves this problem. Okay, so what we propose is to return a result sub-database. And I want to show you a little bit how this works, what the approaches are, and what you can do with that. So what we do is we take the statement here, the existing SQL statement, but add a keyword to that, saying result to be. And that means you don't return a single output table, but you return separate tables, each table that's mentioned here. So I'm mentioning 3 tables here, so professors and give and lectures. So I would return 3 relations, and from each relation, I return those tuples that are part of the original result. So I don't combine those tuples like in the standard single table query statement, but I just identify the tuples that are important in the join result, that contribute somehow to my join result, but I don't force them into a new relationship, so to say. Yeah, this is the single table SQL query forces tuples into new relationships, whether they want it or not. So I'm not forcing anyone into relationships here with this approach. Yeah? Pun intended. So basically, the result here is something like that. Yeah? So you see, okay, you get these relations. Actually, you only get the dark gray tuples. Yeah? So you get 3 relations returned, and each only returns the gray tuples here. That are the ones that take part in the query. Here's another variant. You could also return it as some sort of dictionary, where the result is not just an iterator of tuples or list of tuples, but for each participating relation, there's a bunch of tuples that qualify. Yeah? So that is a subdatabase. That's a subset of the relations of the underlying database. And for each relation here, it's a subset of the tuples, a subset of the tuples that participate in that join. Yeah? That's how we define this join result. Yeah. And the interesting thing is if you do that, you solve all of these problems at the same time. So you don't have denormalization. Why? Because I don't combine tuples from one relation with the other. I do not introduce any redundancy. I keep the tuples as they are. I just return the tuples that take part. If I have a question about the schema, well, I don't touch the schema. The schema is exactly the same as the relation of the underlying database. If I want to have information about the schema professors, yeah, look at the database. That gives you exactly the information. What are the keys? So all the keys are preserved. All the unique constraints are preserved, of course. Yeah? So there's no relational or key information loss for this stuff whatsoever. Yeah, and this object stuff, okay, maybe that goes too far here, yeah? But basically, I would claim it's the same thing, it's all solved. Yeah? Okay, and now we look at a couple of algorithms, how you would approach that. And that's a very, so how we approach that is a very generic idea you can do in database systems. So in database systems, it's always like, oh, this is not really done well. Okay, how could we fix that? How could we integrate that? And the good idea, or a very good approach, is often you use an existing system somehow. Make your life easy. Yeah, don't start everything from scratch, because database systems are huge beasts. You should always think about, can I leverage that? Can I exploit the existing stuff without having to reinvent everything myself? Huh? And we do that in both approaches. But there are 2 classes of approaches here. So the one is really, okay, black box. What if we only have SQL? What if you don't have access to the source code? Like for a commercial database system, you don't have access. How can we simulate something like that? Versus white boxing means, okay, now we have access to the source code. How can we hack it into the database system to make these things happen? And we will first look at the black box approach. So the idea here is we take this incoming statement that has the result DB statement, we catch it. We don't send it directly to the database system, but so basically it's again a wrapper architecture, yeah, if you think about it in design patterns again. So what we do is, of course, if this is the interface of the database system, what we do is we provide a wrapper around the interface that actually returns that sub-database, but then we have to do something and use this interface. So we send SQL queries to the unmodified API of the existing database system, but we wrap something, we do something around that to simulate our functionality. Yeah, so it's a typical wrapper approach. So how does it work? So there are actually 4 different rewrite strategies. They're actually a bit more, but I think it's enough to get the idea. So this is rewrite method 1. That basically means, okay, so I have a query, the SQL query I want to execute. That's the one I showed you here. That's basically what I mean by unmodified query is this query without the result DB. That's a valid standard SQL query joining these 3 relations and doing this filter. That's what I mean by existing query. Yeah, so every database system can execute that. Yeah, and that's what I mean here. So basically, I run a transaction, begin and commit, and within the transaction, I execute 3 SQL queries. I take the unmodified query here, yeah, what I showed before in each and every case. However, I do a select distinct to the attributes I want to have. So what does that do? What does that transaction do? Yes, this existing, not called unmodified rest of the query. That's the existing SQL query without the result to be joining three relations and returning a result set. It's always the same. I execute the same query unmodified 3 times, but I just project differently. Huh? First is projecting to the attributes of P, then the attributes of G, and then the attributes of L. And I use distinct, meaning, okay, each combination of these attribute values is returned only once. What does it do? And why is it wrapped in a transaction? No idea? If you go back to what how I defined this problem. So I want to return something like this. So for each relation, I want to return the tuples that take part in the result. So how would I compute the tuples that take part in a result? Yeah, in the existing query, okay, I get something like that, and I get this combination where the professor name is repeated. I showed that previously. But now I want to have each and every tuple from P in the result only once. So how would I do that? I can also do that in relational algebra, yeah? Louder, please.
Exactly what we're doing in the code. We just do the normal join result, and then we project out the
Yes. Exactly. That's exactly what we do. If we do the standard stuff here, yeah, so basically run the query as is. However, from that query, we don't take these long tuples, but we only project to the attributes of P, including its primary key, p.id, yeah, making it distinct. So that means I get each and every tuple from P that takes part in the result set of the single table. Yeah, and I do that for each relation I want to have. It's only 3 relations here. If I had n relations, that would be n different queries. Like that, I compute a subdatabase. So each query computes the result for one of the relations, reduced to the tuples that take part in the result. Yeah? That's basically one way of doing it. Then the other is you materialize. So materialized view basically means, so we had views already in the undergrad lecture, and I already warned you never use materialized views. Here we're using it as a hack. What this is doing is basically it executes the existing single table query. That's what it's doing here. And the result is stored physically as a new table. That's what materializing means. Yeah? So standard view would not execute a query, here only when it's being used in another query. But some systems support this materialized view, which really means, no, if you create a materialized view as a query like that, then this query will be executed directly, and whatever the result is, it's going to be put into a separate physical structure, a new table. That's a materialized view. Yeah? And doing so, I do something like this. Yeah, now I select distinct, again, on the attributes I'm interested in. I forgot, did I forget something here? Here I selected also H, that doesn't matter. Here also doesn't matter, just, okay. Doesn't have to be H, whatever. If you want to have H, you can also select H here, but then you also have to select H here, of course. And it's just the 2 attributes from P, it doesn't matter, but in spirit, it's the same idea. Well, what is the difference here, and what is the advantage? And if you attended the first hour of our lecture, yeah?
You only execute the query once.
Yes, you execute the query only once. Yeah, potentially in the first approach, you might have executed it 3 times or number of relation times. That's true. What is the price you paid, potentially? Yeah?
The database system needs to materialize.
Yes, needs to materialize, needs to put it on SSD disk and whatnot, in particular for big tables. For this super tiny table, it doesn't make a difference. It sits in my memory, there's no extra costs. Very good. And what about these next 3 queries? Yeah, so each query does the stuff basically reads this materialized table. There's no joins involved anymore. The joins happened already when materializing. But now it projects out and has to remove duplicates. Remove duplicates through a hash table or something like that. Yeah. What happens here is the price you pay in this part, or something you could do about that. Yeah? It's louder. Yes. Yes, yeah, so it could be in the worst case, it's a super big materialized view. You have to scan it multiple times. Yeah, again, think about the example from the first part of the lecture where we scan a petabyte of data. We do that once, we do it twice, we do it 3, twinker, twinker. So what could you do? Yeah?
So we are going through the same exact table 3 times.
Yes.
And we can page the 3 queries as we did.
Yeah, we could somehow try to execute these things together. In particular, if there were an interface signaling to the database directly, hey, I have these 3 queries, they all read the same table, by the way, it's just slightly different stuff we're doing. Here it's not a filter condition, here it's a distinct operation. Still you can do multi-query processing. Still you can do something along the lines, aha, for each tuple that I read, I deliver it to 3 consumers that do something with the tuple. Rather than just 1 consumer. On 1 query, you can do 3 queries at the same time. Yeah? And you will be doing something like that in the assignments. So if you do the assignments, you will be doing. There's an extension of the shared scan idea. It gets a bit more involved if it's not just where clauses, if it's not just filtering. You can still do stuff. You can still share work in different query plans. And that is what one of the assignments of this week is about. But today's Wednesday, so it appears on Friday. Yeah? Anyway, but when it appears on Friday, you will see. Okay, right. Here's another variant. That is rewrite method 3. So that's without any materialization. There's no create materialized view whatsoever. But what I do here is something like that. I do a subquery. Yeah? Inside this subquery, maybe just look at this one. It's kind of interesting how you do it here. You could actually do it differently. But to start with, I think it's a good start. So I do something like that. I do a join on G and L only. So basically, I'm just taking the part of my original query affecting G and L. Yeah? And then I use it as a subquery saying, okay, from professors, I want to have all of those tuples where the PID is in this result set. Yeah? And if you look at the other queries, it's all mirrored. Maybe if you look at this first, this is just the query affecting P and G. It just joins professors with give, and then it returns everything from L, where L is in that result set. That's the inverse operation in a way. And then there's this table in the middle, this give table. It's doing like that. It takes all the tuples from G, where the PID is in the professor's relation, and at the same time in the lecture's relation. Yeah, so that's a subquery. But what is the difference to what we had before? does the same thing, just in different sequel. Yeah? Just saying, okay, I want to have a subset of that relation. That's what this is saying. This is saying I want to have all the tuples from P, but just without duplicates. The PID already, it should also actually make a duplicate free already here with that. But actually you're saying, okay, I want to have those tuples from P that qualify under a certain condition. That qualify under the condition that the P.id is used somehow in the remainder of the join of G and L. Yeah, so that's a different way of doing the same thing. It's saying, okay, I want to have those tuples from P that participate in that join where G and L are being joined under that condition. It's a different way of computing the same result through subqueries. And when you evaluate that in a system, you see that may lead to different plans, different execution times, and whatnot. More details are in the paper I'm linking here. So method 4 is again materializing. It's again materializing the join over all of those, over materializing this individual query, the single table query result. However, now what I'm doing is I'm just materializing the P and L ID columns here. And then when I want to compute, for instance, everything that takes part in G, it's just returning the materialized view. When I want to return the subquery approach, I can basically replace the subquery by the materialization I had here. So basically, I'm materializing the G table reduced by the tuples that take part. So I just pick from this GIF relation the tuples that take part in the actual result. That's the trick I'm playing here. But again, it returns the same result. Yeah. So if you ask which of them are relevant for the exam, maybe not all of them, let's be fair. But you should understand rewrite method 1. You should understand rewrite method 2. Yeah, 3, okay. Maybe you should know that, okay, what this has to do with what's called a semi-join or semi-join. We will go there in a moment. Okay, so the more interesting thing here is actually, so that is a black box approach. And now we look at what that means if you go into a white boxing approach. How do you evaluate a query like that if you have acyclic query graphs? So query graph again is you have your query, you specify a number of relations. So here this graph represents a query where there's one node for each relation being mentioned in the query. So R, T, S, and U are the relations being mentioned, and that is my query graph. And now what I do is, those are the nodes, and the edges I put into this graph if there's a join condition. So the edge between T and S signals, aha, in the query, in the SQL query, there was a join condition. Could be T.id equals S.T underscore ID or something like that. Yeah? So whenever there's a join condition, I put an edge there. If there's no join condition, I don't put an edge. If there's no edge, that actually implicitly means that's kind of a cross product. Yeah? So we talked about that at length in the undergrad lecture, actually. It's more like a reminding you. Yeah? And now what the algorithm does in whiteboxing is that we have this graph, and an important property here is that this graph is acyclic. So there's no cycle in this graph. I will later on explain what to do when the graph is cyclic. So what we do is we pick a node. If you have a graph like that, an acyclic graph can easily be converted into a tree by simply picking a node. Yeah? And that's what I'm doing here. So I have 4 possibilities to pick a node. Here I pick R as a root node, and that induces a binary, induces a tree, not necessarily binary, but induces a tree. Yeah? So this is a tree that is induced if I pick R as a node. If I pick S as a root node, that's a tree. If I pick U as a root node, that's if I pick T, that is a tree that's being induced. Yeah? That's step 1 of the algorithm. So in step 2, I mean, that's already an enumeration problem. Yeah? So for practical purposes, the question is, okay, which root do you pick? You can do that randomly, but if you map all of these problems to cost-based optimization, of course, it will happen that this may have different costs than that plan. Yeah? If you start with this as a root node and that as a root node in the algorithms, that may lead to different costs. So it's not that easy. Yeah? I'm just saying, okay, there's a space, there are different options to run these queries, and so different options to convert this acyclic graph into a tree. Yeah? And each option comes with different costs, of course. Yeah? And there's also the option here that the problem that the children, the order of the children nodes may matter. So here I depicted it as U is on the left and S is on the right. Yeah, as in standard query optimization, that may make a difference in physical planning. So it might be that having S on the left and U on the right is better. Fix my shoelaces here. Yeah, so there's a huge space of possible plans that is generated just in this single step. Huh? And this is called the root node enumeration problem. Yeah, then how do we actually now execute that in an algorithm? Yeah? Without doing the SQL magic, the SQL rewrites, now we have the option to actually run an algorithm. And that's what this visualization actually shows. So we have chosen R as root node. And this stuff here, I have it on the next slide, I guess, that's a filling level. That's indicating, okay, this R still contains all of the original tuples. All of the tuples from R are still available. Yeah, that's this stuff. This indicates, okay, some of the tuples from T were removed. So I removed some of the tuples, just a subset is available. And what I will be executing in the following is a cascade of semi-joins. A semi-join, I wrote the definition here as a repetition again. It's just the inner join projected to the tuples from the left input relation. That's the left semi-join. Left semi-join because here it is closed. And there's also right semi-join. Yeah, if you look at this, that's the left semi-join because here this is closed. Here it's open. That's a difference to the standard join symbol we use. So the left semi-join answers the question, if I executed a join of the relations R and S, which tuples of R would be part of the result? That's exactly what I want to have. Yeah? So it's exactly solving this problem. So which tuples, so if I did a standard join on R and S, which tuples would take part in that join? So basically the select distinct we did above, projecting just to the tuples from R. It's exactly the same thing here in relational algebra. No difference whatsoever. Yeah? Okay. And now what I do is I do a bottom-up and a top-down pass over the tree. And that's called the Yannakakis algorithm, which is interesting because it was kind of also simultaneously developed by a guy named Phil Bernstein, very famous guy in databases. But everyone calls it the Yannakakis algorithm. I don't know. Yeah. Okay, and I will briefly explain that one. So do we have time for that? I think I make one round and then I repeat it next time anyway. But the idea is that you run over the tree and start here with relation U. So that's what the arrow indicates. Now I compute the semi-join of T and U. I reduce T by the results of U. So I do a join of T and U projected to the tuples from T. So in a join of T and U, which tuples of T would still survive? And that is T prime. Yeah, that's what I show here in the middle. Yeah? That's step one. Then I do the same thing with the S input, already using the T prime I used previously. That's already the reduced T prime. Now I semi-join with S and reduce T prime prime even further. Yeah, I get less tuples. And then I run up the tree. Now I reduce R by T prime prime. So the number of tuples of R get down. So basically now the information spread from U and S up the tree. However, R was reduced and T was reduced, so I still have to spread down the information once. I have to do top-down pass, and that happens in the next step. Now, as R is reduced and was informed by all other relations, I now compute a T prime prime prime, or T prime 3, however you name that, reducing T with the results from R. And then I reduce U again with all of these results, and I reduce S again with all of these results. And the result of that is the filtered relations, and that's exactly the result we want to have. That's a sub-database. That's 4 relations containing just the tuples that take part in that join. Yeah, and that's called the Yanakakis algorithm. Okay, with that we will continue next time. So see you on Friday. Yeah? Thanks.